Uh, Today we will discuss the geostationary satellites. Geostationary satellites. These satellites are sometimes also known as parking. Their orbits are known as parking satellites, and they are also stationary with respect to Earth. Why we call them the geostationary satellites? Geo means Earth, and stationary means at rest. Since they are at rest with respect to a particular point in the Earth, and that's why they are known as a geostationary satellites. Actually, they are not at rest. They move as the Earth moves, but since with respect to Earth, they are stationary, so they are known as geostationary satellites. For example, if this is the Earth, and this is the orbit of the geostationary satellite, sometimes also known as geosynchronous satellites. Geosynchronous satellites are means they are synchronous with the Earth, so they are known as geosynchronous satellites. And this orbit is known as parking orbit because the satellites are just parked in that orbit. That orbit is fixed. This orbit is a fixed height. This is the supposed satellite here. This is the geostationary satellite. Now, suppose Earth moves from west to east in this direction. Suppose as the Earth moves, similar is the case this moves. So, if this particular point is at Earth A, and this satellite seems to be here, when Earth rotates and its A point comes here, this geostationary satellite also comes here. So always with respect to a point, this satellite seem to be stationary because actually these satellites are used widely for the telecommunication purpose. So they are very useful for broadcasting of these matches, the programs, other things, and the live other things. So many various telecommunication purpose for this one. So these are the geostationary satellites. Now what are the properties of the geostationary satellites? First property is they seem to be stationary. They are stationary with respect to Earth. They are stationary with respect to a position on Earth. You can say that one, a position on Earth. First property. Second property is they move in same direction as Earth moves, that is from west to east. They move from west to east. Third property is they have the same angular speed as that of Earth. It is quite clear. Suppose if this Earth completes a point, reaches from here up to this one, this will also completing its circumference or its path. So clearly, first property is stationary with respect to position on the Earth. Second is they move in same direction as Earth moves, that's from west to east, and they have the same angular speed as that of the Earth. These are the three properties. The fourth property is they have the time period of that of Earth. If they have the same angular speed, of course, then their time period must be same. So they have the time period of 24 hours, because Earth completes its one round around its own axis in 24 hours. So this satellite also has a time period of 24 hours. Means after 24 hours they will always be they will complete their one complete revolution, or one complete circle, or one complete cycle. Fifth one is they are usually placed in equator, in the plane of the equator. They are placed in a plane of equator. That's very much important. Why they are equator? Because suppose if this is the Earth, they are actually plane in this orbit. If this is the equator, it's three-dimensional. So if they are placed in equator. Why they are placed in equator? Because Actually they always remain stationary with respect to Earth at a particular point. If they are not placed in the plane of the equator, then there may be sometime more distance when the satellite is on North Pole, or more distance when it's on South Pole. So there is more distances in the satellite will no more be stationary. So that's always the case that they are placed in a plane of the equator. Now let us drive some basic things of this geostationary satellite. First is, let us see what should be its angular speed. When these geostationary satellites are placed, they have the time period of 24 hours. So I can find angular speed of geostationary satellite by simply, you know, that T is equal to 2 pi upon omega, or omega is equal to 2 pi upon T. Now you put the values 2 into 3.142 upon T is 24 hours, 24 into 3600 seconds. You have to change in seconds, and now you have to calculate this. If you calculate this, this coming out to be it is coming 7.27 into 10 power minus 5 radians per second. This is the angular speed of the geostationary satellite. It's very simple. You can just calculate angular speed. You know, it's always a formula. T is equal to 2 pi upon omega. So omega will be equal to 2 pi upon T. So when omega is equal to 2 pi upon T, now you can say 2 into pi is 3.142 divided by 20, this T is 24 hours. So I'll make it in seconds. 24 into 3600, it becomes 7.27 in 10 power minus 5 radians per second. This is the angular speed. Now suppose if I want to find the linear speed of such satellites, what should be the linear speed of such satellites? If I suppose I want to find a linear speed, but linear speed requires first of all the orbital radius. So first I'll find the orbital radius. What should be the orbital radius? Orbital radius, you know, it is the distance from center of the satellite up to the center of this one. Suppose this is R. I'll go for the golden equation. Golden equation tells us that mr omega square is equal to gmm upon r square. M is mass of the satellite, r is the orbital radius, omega is angular speed, g is this is the gravitational constant, m is mass of the earth, this m is mass of the satellite, and r is orbital radius. So this m is cancelled out. So the mass of the satellite, mass of the geostationary satellite doesn't matter for their orbital radius. So I want to find orbital radius. So r cube will be equal to gm upon omega square. So r cube, g is 6.67 into 10 power minus 11. Mass of earth is 6.0 into 10 power 24 upon omega square. Just we have calculated, the value is 7.27 into 10 power minus 5 square. This is the value of r cube. Now you have to find the r cube. Calculate this. This 6.67 exponential minus 11 into 6 exponential 24 divided by 7.27 exponential minus 5 and its cube. Sorry, it's a square. So this 6.67 exponential minus 11 into 6 exponential 24 divided by 7.27 exponential minus 5 square. This coming out to be 7.572 into 10 power 22 meter cube. Now you have to find the cube root of this, and if you find the cube root of this, the cube root of this, it comes out to be 42306.076 meters, or almost it is 42,000,000 meters. It is, I can say, 42,000 meter almost kilometers. Almost is 42,000 kilometer. in up to two significant figures. Up to two significant figures, it is 42,000 kilometers. Now, if this 42,000 kilometers, sometimes examiners ask, they say, give this radius in give this orbital radius in the form of the RE, or radius of the Earth. If they found they ask for that one, you can calculate this way. You can say R is equal to, let us take this one now, figure 4230676 multiplied by RE and divide it by RE. Now this becomes 4230676 upon, now put this value of RE, 6.4 into 10 power 6 into RE, and you get divided by 6.4 exponential 6, and you get 6.61, 6.6 RE almost. So we say orbital radius is 6.6 times the radius of the Earth. Orbital radius of the geostationary satellite is 6.6 times the radius of the Earth, or it's almost 42,000 kilometers. Orbital radius is always the distance from center of the Earth up to the center of the pole. So that is the orbital radius. Now I can find, examiners usually say, find the height of the geostationary satellite. Height of geostationary satellites. When you find height h, it's always orbital radius minus RE. So I can say, in terms of RE, I can find this is 6.6 RE minus RE. So height is 5.6 RE. Means height of the geostationary satellite is very huge. It's 5.6 times the radius of the Earth. Now I can find it in kilometers also. I can say almost about 42,000 kilometers minus radius of Earth is 6,400 kilometers. So this coming out to be, I think, almost 36,000 kilometers, 35,600 into two significant figures. Almost I can say it's 36,000 kilometers. Almost height in two significant figure is 36,000 kilometers. You can work for the actual exact values by do not rounding it off. So this is the height of the geostationary. Now one thing as a caution, as an experienced teacher, I tell you, sometimes examiners say calculate the height of the geostationary satellite. Do not take this one. Suppose this is Earth. This is Earth. I'm sorry. This is Earth, suppose, and this is the geostationary satellite. You take this RE and take this as H, and you just put the equation M into RE plus H omega square is equal to GMM upon RE plus H whole square. If you take this one, this is also okay. But then it will require a very huge calculation, and it's a very difficult thing. So do not try this one. Do not try this equation. You can get, but the calculation will be very difficult. It is better for the height first to calculate the orbital radius. First always calculate the orbital radius, and then subtract the radius of Earth from it, and you will get that one. Now I can find also the linear speed of the geostationary satellite. Now what the linear speed of the geostationary satellite? I can use V is equal to R omega. Now R is 42,000 kilometers. I'm using approximate values is 4.2 into 10 power 6. 42,000 kilometer means, let us see, 42,000 into 10 power 3 into omega is 7.27 into 10 power 5. So it's almost 42,000 kilometers, 42,000 exponential 3 into 7.27 exponential 5. It is coming to be 10 power minus 5, sorry. So it is coming to be 42,000 exponential 3 into 7.27 exponential minus 5. It is coming as 3503 meters per second, or in kilometers it is 3.1 kilometers per second. So linear speed of the geostationary satellite is approximately 3.1 kilometer per second. It's not a small speed, it's a very huge speed. You can think about in 1 second, in every second, it is covering a linear distance of 3.1 kilometer. That's why it completes around the Earth in 24 hours. So this was the geostationary satellites. Now its uses, I tell you, this is also used for the spying purpose for the particular area, and it is also used for the telecommunication purpose, especially the television programs are broadcast due to this one. Now the question rises sometimes is, people say, okay, how many such satellites are needed? How many such satellites are needed to cover the entire world? Now you'll be amazed to listen. You may be thinking that there may be some 1,000 satellites, some this one, but that's not the case. Only 3 satellites. If this is Earth, now all the geostationary satellites are fixed in one orbit. They do not collide because they are moving with the same speed. They are, suppose if any country has 3 satellites separated at 120 degree each, they are enough to cover even every inch of the Earth. So only 3 satellites separated at a distance of 120 degree are enough to cover the entire world. And sometimes examiners say why these satellites, there are so many satellites from each country of the world, so they do not collide. Actually, suppose this is the position of one satellite, this is another position, this is another position, they have a fixed position. There is an institution which governs these positions and assigns the position, but see, if the positions are fixed, their speeds are fixed. Suppose when this comes here, this moves here, so the satellites will never collide with each other. Sometimes you will ask that question. So what we learned about the geostationary satellites, I am just now making summary of this one. First of all, these satellites are known as also synchronous or geosynchronous satellites, and their orbits are known as parking orbits or parking orbits because they seem to be stationary. Why the name of the geostationary satellite? Because they seem to be stationary with respect to the Earth at a point. That's why they are known as geostationary satellites. What are the properties? The first property, of course, is they move in the same direction as which the Earth moves. That's from west to east. That's why they seem to be stationary. When the Earth moves, they also move in the same way. They have the same angular speed. They have the same time period as that of the Earth, but linear speed will be different because the radius of the Earth is different, and the radius of the geostationary satellites, the orbital radius of geostationary satellites is different. So the linear speeds will be different, but the angular speeds and time period will be same. And we have found the time period, angular speed by the formula omega is equal to 2 pi upon t, and just to put the values 2 into 3.142. This is 24 hours change in this seconds, and its value coming out to be, I think, 7.27 10 power minus 5 radians per second. This is the angular speed. Now sometimes you have to find, suppose this is one of the property, angular speed. Other property is they always must be placed in the equator, the plane in which the equator is. Suppose if this is the Earth and this is the equator, on one side, on this side, this one, these geostationary satellites must be placed in this one, so the distance from their center of the Earth remains constant. Otherwise, if they are placed in this other orbit, their distance will not be constant. I have also shown for simplicity in one plane. Actually, when I have shown this, I mean this is the equatorial plane. The equator is, but actually you can draw in this way also, but the drawing is difficult, so in order to have the easy drawing, I have just gone for this one. Then why they are placed in equator? Because if they would have not been placed in the equator, sometime they may be on the North Pole, sometime may be on the South Pole, and distance will be different, and they will not be moving with the same angular speed as the Earth, and they will not be no more be stationary. So in order to have the stationary or to be specific for some point, to be particular for some point, they must be placed in equator, in the plane of the equator, number first. Second, sometimes examiners ask find the height of the geostationary satellite. Height of the geostationary satellite is fixed, and that orbit is fixed. But when you calculate the height First of all, you have to calculate the orbital radius. Without orbital radius, you will be unable to calculate the orbital height. So for orbital radius, suppose R is the orbital radius, I can say mr omega square is equal to gmm upon r square. So now this will be m is cancelled. So r cube will be equal to gm upon omega square. Now put the values. G is 6.67 10 power minus 11. M, mass of the earth, is 6 into 10 power 24. Omega I have just calculated, 7.27 10 power minus 5 square. This is r cube, and when you have to find the cube root, it comes almost 42,000 kilometers. Up to two significant figures. So orbital radius 42,000 kilometers. You can express in terms of RE. You can multiply, suppose, by RE and divide this by, suppose, 6,400 kilometers in kilometers. Then this comes out with 6.6 RE. So orbital radius is almost 6.6 times the radius of the Earth. From the orbital radius, you can calculate the height. Height will be just 42,000 minus this 42,000 minus 6,400. That's in kilometers of the Earth. So this comes out to be height almost is 36,000 kilometers almost in two significant figures, and this height in terms of R will be 5.6 RE. Okay, now I can calculate the linear speed. The linear speed is now simple. You can calculate V is equal to R omega. V is equal to R omega. Just see V is equal to R omega and put the values. R is 42,000 10 power 3, omega is 7.27 10 power minus 5, and this is almost 3.1 kilometers per second. So this is the linear speed of the satellite. So you can calculate in that way.